and the supersymmetry is the extension of the symmetry, including the exchanges of the fermion and the boson. And the other motivations of the supersymmetry, or so-called the SUSY, is the solution of the hierarchy problem of the Higgs boson mass. In the standard model, the Higgs mass get the loop correction by the fermion. For example, this dotted line represents the Higgs, and here is the fermion, and this fermion loops gives the quadratic divergence radiativity correction. And to get the observed values of the standard model Higgs, this value is roughly the 125 CV, and the loop correction is quadratic, and this cutoffs the integral is up to the Planck scale. So the tree level, the bare mass term of the Higgs mass should be the fine-tuned to get the electroweak scale of the Higgs mass. So that this bare mass term should have the Planck mass plus the electroweak scale. This is quite fine-tuning, and this is called the gauge hierarchy problem of the Higgs mass. And the supersymmetry can resolve this because now the fermion, the superpartners of this fermion, gives additional correction, but the opposite sign. So this can offset the radiative corrections with the quadratic divergence by starting this equal coupling, and the Corti coupling has a similar scale. And still the such a supersymmetry can resolve the gauge hierarchy problem, but the such a fermion can give the additional corrections in the logarithm corrections by the for the standard model Higgs. And many supersymmetric model gives the different corrections for this logarithm form by the fermion. And this depends on the SUSY breaking model, and also among the various fermion, the top quark gives the dominant contributions on the standard model Higgs, because equal coupling is the last compared to the other first and the second generation. So the corrections are following for the MSS, because there are two Higgs developed. So the standard model Higgs is also determined by the angle betas, whether this tangent betas is defined by the ratio between the up type Higgs and the down type Higgs vacuum expectation value. So this is just a tree level from the two Higgs developed model, and we can get the logarithm correction. So this logarithm corrections comes from the top quark and the top quark or stopped quark. So these top quark structures generate this loop correction. So the mean values of the stopped quark mass is important. This is denoted by the capital mass, and in the denominator this is just a top quark mass. And also the additional term, which is the stopped mixing parameters, the xt, is also important. This gives additional correction term for this logarithm function. This stopped mixing parameters that are related with the a term of the top quark. This a term is a SUSY breaking term, so in the Lagrangian there is explicit breaking through this a term, like as this form. ER, TR, and H's. And this top mixing parameters actually mixed between the left-handed and right-handed one. So the important parameters to determine the standard model Higgs correction on the mass is the angle, the betas, and the stop mass, and the stop mixing parameters xt. There are the three parameters in here. And depending on the SUSY breaking model, the behaviors of these three parameters are quite different. So now I will talk about how the several SUSY breaking model can give these parameters. So for example, to give the observed values of the SM-Higgs mass 125 CV, the stop clock should have the TB scale, or because this m just the cosine scale 2 betas is roughly is the 8 GB, because m jet is around this 8 GB or 70 GB. So we need additional corrections from the stop correction. So this stop clock mark should be the TB scale, or this stop mixing parameters xt should be the maximum. So this t scales of Rama scales is roughly root 6. And the tangents beta should not be enough, should not be small. This should be the large enough. The lower bounds of the tangent beta is roughly the 0 or the 4. If the tangent beta is too small, then the Higgs mass cannot to be beat the observed value. So the point is there's three parameters: tangent beta, stop mass, and the mixing parameter. This should be the all large enough, like the TB scale or maximal mixing, or the large enough tangent beta. But the generations of these parameters are quite different for the SUSY breaking model. For example, the some specific model does not provide the item, so the scalar mixing parameters xt is almost balances. So to explain the standard Higgs model, the tangent betas or the stop clock mass should be very large. But such atoms may vanish at the mass in just higher scale, but the atom can generalize in the radiatively by the R's learning. So there are various supersymmetry breaking scenario. We want to get the standard model Higgs values as 125 CV, such an interval. For example, the well-known SUSY breaking scenarios, the example is the gases mediated SUSY breaking or anomaly mediated SUSY breaking. Briefly, is written by the GR must be or IR must be. In these scenarios, the atoms are quite small at the messenger scale, so the star mixing parameters is also small in also the low energy electroweak scale. So the to beat the 125 dB Higgs mass, then the minimal supersymmetry is with the J must be and the A must be is the quite disbelievable. I want to talk about some A must be in detail. Why the atoms are smaller than the A must be. The SUSY breaking term in the A must be is generated by the superconformal anomaly, rather than the direct coupling through with the hidden factors like as the J must be. So as a result, the atoms are not three parameters, but this is determined by the RG equation. So the atoms are determined by the beta functions coefficients and the Yukawa coupling with the gravitational mass. And these beta functions terms are suppressed by the one-level correction, so the atoms becomes smooth for the AM must be model. In the gravity mediated, like as M-Sigma models, is the quite different. There are several parameters in the M-Sigma. The soft mass term M0 and the gauge mass term M1 half, and the atom scale, the A0, and tangent betas and the sine of the mu. Also, the M-Sigma can be classified as the several models. For example, the neo-scale model constrains MSS or very consensus model on universal Higgs models, or impose additional boundary on the high scale subterm. These detailed graphs can determine this specific parameter region to give the Higgs mass values for the observational value. But still the GMSB can alive, because if the stop clock mass is quite large, like as 3 TeV in the split symmetry, so the stop clock mass is the some 100 TeV scale, and other so the particles are split mass spectrums, and this can explain the Higgs the mass. The gauge nodes and Higgs inner mass is in the electronic scale. And also we can consider the high scale supersymmetries. All the superparticles, including the fermions and the gauge nodes, are in the 100 TeV. This is decoupled to the electronic scale. Now we talk about some other topics related with the supersymmetries and the Higgs octets. Until we talk about the one-level correction, but the high order level corrections on the Higgs mass should be important. For example, in the two-loops level, the additional corrections arise from the top cork couplings, and also the QCD coupling, and also the Yukawa interactions. Such a two-loops effect is very important. The one loop and the two loops results the quite difference for the Higgs mass correction. For example, if we plot the one loops or two, then the Higgs mass scales is quite difference over some specific parameter space. Also, the vacuum stabilities of the Higgs potentials are important. For example, the trilinear term, the A term, can provide some spontaneously breaking for the scalar potential for the both Higgs and the superluminous field. For example, this is item with the trilinear scalar coupling. This cubic term can provide the deeper minimum. So for example, if there's a potential, then because the very large linear coupling, then there might be the additional minimum. So the original minimum becomes the Bose vacuum or metastable vacuum. So there might be the quantum tunneling. So to avoid such a deeper minimum, the atom should be not too large to ensure the vacuum stability. If this condition is violated, then this electroweak vacuum is metastable, and there might be the quantum tunneling with such a light. Such a quantum tunneling light should be small enough to avoid the transition between the vacuum, and to give that this actions in the exponent should be large enough. This corresponds to the lifetimes of the vacuums is longer than the ages of the universe. Also, not only the superpotential, we can also consider non-holomorphic supersymmetry, like as there is the daggers of the complex conjugates of the Higgs term. This is the non-holomorphic term, like as the color potential. Also, the second term, the mu primes, the independence to the surface's variable mass. So both terms are non-holomorphic. And this non-holomorphic term can modify the mass spectrums, like the superluminous mass matrix, or the coupling between the Higgs and the superluminous. So for example, here the T prime, the mu, which is a non-holomorphic term here, T prime and the mu prime, can provide additional contributions for the left light mixing parameters of the stop clock. So this changes the standard model Higgs boson. with the some MeV scale. Also, we can consider the decay through the Higgs of Higgs standard model Higgs and the heavy Higgs to the particle. For example, the specific decay channel is this is a standard model Higgs, heavy Higgs, CP-odd, and the charge is scalar. This can decay the neutral linears chi 0 through charge in chi plus minus. Some decay channels might be kinematically allowed or forbidden depending on their mass spectrum. For example, if there's some specific Higgs boson, whether this is some heavy or standard model or CPO or charges one, this can be decayed to the pairs of the neutral and charge, and this decay light is given by the following form. Now here's these apps determined by the mixed matrix of the neutral and charge mass, and this is the kinematical term. If the Higgs mass is the small compared to this pair of the neutral charge, this term becomes zero or negative, so the becomes forbidden, and also the other contribution. For example, if this Higgs is a standard model Higgs and the decay to the light is neutralino pair, then just effective coupling from the neutralino mass matrix is following. So this chart is a neutralino mixing matrix. So we can observe that to get the size of effective coupling, both the gauge component Z11 and Z12, where the binary and the winner component, and also the Higgs component should be large enough to get the non-balancing interaction. But so the standard model Higgs decay is the quite restricted of the parameter space. But in contrast, the heavy Higgs boson can decay to the neutral inner charges pairs, and it can be sizable. So now we talk about the Higgs factors in the supermatrix with the various considerations. For example, the observed Higgs boson mass to observe 120 watts GeV of the standard model can be strongly constrained by the several supermatrix breaking model depending on the like as the J must be, A must be. These are determined by the step clock mass and ATM and the tangent beta. So there are the gravity gauges and anomalite mediated model, and we can give the additional correction like as the two high order one, and we should also consider the modifications from the large items, vacuum stability, and also we talk about how the Higgs can decay to the supersymmetric particles as additional proofs for the supersymmetric phenomenology. Some contents are related with some Laplace, like as the various one on the supersymmetries and the Higgs factors. I see.